we're going to look at some examples using U-substitution to evaluate some indefinite integrals. All right, so we learned already to find some basic antiderivatives of functions that we already know. So we know some derivatives, which means we can turn that around, and we know some antiderivatives. This is not one of those that we actually know, so we're going to use this technique, U-substitution, to evaluate this integral. U-substitution is essentially a mechanism for undoing chain rule. So often, you're going to start by letting u equal some part of the function. Often, that is the inner function. Not always, but often that is an inner function. All right, so when I look at this expression here that I'm trying to integrate, I might notice that I have an inner function. Inside the exponential function, I have an x cubed function. So I have the x cubed function inside the exponential function. So for this problem, that would be a wise choice to let u equal. And at the beginning, it will be fairly easy to figure out what to let u to equal, often an inner function. We'll get to some harder problems where you have to be a little bit more creative to figure out what to let u equal. But that's a good place to start. If you see a function inside another function, that might be what you start with. All right, and then the next thing that you want to do is find du. So you have to remember definition from the section that we did on differentials, that du, here I have u as a function of x, so du is defined to be du dx times dx. It sort of looks like those dx's should cancel. This isn't exactly a fraction, so they don't really cancel, but we like that notation because it looks like those dx's should cancel. So from my u that I chose here, I'm going to find the du. All right, so du will be the derivative of this function with respect to x. Derivative of x cubed with respect to x is 3x squared, and then times dx. So this is my du dx times dx. Right, that's a differential, what we did a couple weeks ago. All right, so there's my du. All right, the key to making sure that you're doing U-substitution correctly is these middle two steps that I've listed out here. Check to see that your u and your du account for all the variables in the expression that you're trying to integrate. Okay, so I have an x cubed here, and that's accounted for by my u. And then I also have, in my function I'm trying to integrate here, 3x squared dx, and that's accounted for here in my du. So we're good on this one. All of the variable parts of this expression are accounted for. I actually have an e here, but remember that's a constant. So all the variable parts of this expression are accounted for between my u and my du. So you want to check to make sure that that happens. And then you want to substitute into the integrand so it is entirely in terms of u and du. So there should never be a step in your integration where you have both x's and u's in the integrand at the same time. I see people write that down sometimes. That's a bad habit to get into and technically incorrect. So the next step that I want to do here is substitute in place of the 3x squared dx what that is equal to. So that is all du. I'll just underline that so we're clear about that du went in place of the 3x squared dx. And then in place of the x cubed, I'm going to substitute what that is. I still have this e here. Right, so I'll just put a little circle around that to indicate that that corresponds with the x cubed that I had up here. Okay, so key steps here. Once you've chosen what your u is and find your du, make sure everything is accounted for and then do that substitution. So notice in the original integration, everything's in terms of x. And now this step, everything's in terms of u. You should never have a step where you have both x's and u's mixed in the problem at the same time. Okay, so hopefully at this point, you've got to a place where it's a basic antiderivative that you know. And this is the antiderivative of e to the u is just e to the u. And we don't want to forget that plus c at the end, which represents all the possible constants that might have gone away when I took the derivative. All right, and then at the end, you want to back substitute so that your answer is back in terms of the original variable that you started with. All right, so this is where I go back to my U substitution, and in place of U, I'm going to put back in place of U what the U is, x cubed. All right, so my answer here, e to the x cubed plus c. So that's the antiderivative of 3x squared e to the x cubed with respect to x. I could verify that this is a correct answer by differentiating this expression. When I differentiate this expression, I should get what I have up here. And you can verify that pretty easily. Use chain rule to find that derivative, and you will get 3x squared e to the x cubed. All right, so this was a pretty straightforward example. There wasn't anything too complicated in managing my u and my du. We'll look at some more examples where there's a little bit more to the middle part here. So I'm going to get rid of all these words over here so we have room to work out some more examples. But we'll look at more examples. These are the key steps that we'll use every single time. So we'll talk about these, but I won't have these up here when I do the more examples. All right, look at some more videos.